let's get started. Did people get my email? You didn't get an email from me? Yeah, to say that the videos were up.
Yeah.
Did you get that email, sir?
I'm looking.
Okay, very good. How often do we check our email? Every day?
I get mine.
Okay.
Yeah, I got it.
Okay, good. That's a good answer. Good answer. Anyone who did not get my email? Anyone who did not get my email? Okay, good. So they're here, right? So maybe we need to turn this down, right? The light. Is that better? And if you like, you can look right there at that screen. I don't know why the hell it does that, but right there. So lecture videos here, PDFs of the lecture notes are there. Okay, so now as I said in the email, do we all have QuickTime? Is that okay? As a format, I have to still answer your RSS feed question. Okay, so I still have to do that, and so it should just come up. I hope. I hope it loads.
Yeah.
Okay. So it works. Okay. Okay. So now let's go to. We're in chapter 5, okay. So we did some approximating areas. We'll do some definite integrals. All right, so we'll open that up. By the way, again, I'm a massive fan of the ebook. Okay, so go in. Are we okay getting into?
Oh, by the way, you don't need the code.
You still don't need the code?
After I bought it and opened it, yes.
Maybe it's just me. Maybe it's just me. No class I've ever taught here have you needed the code. So, you haven't bought it yet?
No, last semester I did and I opened it.
Get in.
That's what I did this semester.
Well, again, I'm sorry.
Good job.
I don't know what to say. So, I don't know what to say. I put up some homework, okay, for section 5.1. All right, so I'll take any questions about anything we talked about so far. Okay, so we're doing, here's what a definite integral is. So here's the notation. We defined it last time. The integral from a to b of f of x dx. Right? And it's going to give us the net area under a curve. Okay. All right. And so again, it's the limit of a sum. Okay. Question number 1 on the exam is define the integral. Define this. Right? And then question number 2 is to use the right endpoint, left endpoint, midpoint method to approximate some function I give you. Okay. So one of the easiest ones, right, just from the context, one of the easiest ones, let's see what we have here. Maple, where are you? You're here. Oh, that's loading. 5.2. So the net area. And we'll do some examples. Right? So the function f of x equals 1 minus x squared on the interval a to b with n equally spaced subintervals, right? So a midpoint method, you can do a left Riemann sum. And all we mean by Riemann sum is just adding up those terms, adding up the rectangles, okay? That's the net area. Here's the definite integral. And it's the limit of a sum. And so for this particular function, can I maximize this? Right, so for this particular function, the left endpoint sum here, from the interval a to b, they break it up into a number of intervals, 6. It seems like 1, 2, 3, 4, 5, 6. Break it up into 6 pieces, and they're using the left endpoint. So for this first piece, again, they take this to be the height of the rectangle. For the second piece, this to be the height of the rectangle, and so forth. The thing to see, of course, is that these two rectangles, right, when you calculate the value of the function here, you get a negative number, right? And so the integral is the sum of all this positive stuff plus all of this negative stuff, okay? Now that's not the integral, that's an approximation to the integral, okay? And so they go in general talking about Riemann sums, okay? So the definite integral, as we defined last time, is the limit as the number of rectangles tends to infinity. All right, so here is the answer to number 1 if you prefer the book explanation. So we'll go ahead and we'll put this in, okay, so. I need to make it bigger, we will. Let's see here. I don't think I can make it that much bigger. Maybe if I bring this over a little bit. Okay, so. All right, so what does this notation mean? Are we familiar with summation notation? Who is not? Someone not. Never seen this sum before. Let's talk about summation notation here. So when I write the sum, I equals, are they using I? They're using K. We'll use K. The sum K equals 1 to 3 of K squared. This symbol here means sum, and so literally what you do is when K is 1, you take 1 squared, and the whole point of this symbol is an operator, and it means you're adding. This is sigma, sigma standing for sum. So it's 1 squared plus 2 squared plus 3 squared. As a matter of fact, we used this sum last time when we were finding the integral of x squared. And for extra credit, you have the integral of x to the third, okay? And so you're going to have the sum K equals 1 to n of K cubed, right? And all that is 1 cubed plus 2 cubed plus 3 cubed plus all the way up to n cubed. Okay. So instead of writing out the sum, the area of the first rectangle plus the area of the second rectangle plus the area of the third rectangle, all they're doing is just adding up all of the rectangles and then letting the number of rectangles tend to infinity. Now, one of the things we should observe, of course, is that this is not saying that exactly. This is saying that the limit is delta tends to 0, right? And I say the limit is n tends to infinity. How do we rectify what I say versus what they say? What do you think delta means in this context? Say it again. It's the change in what? The width of the rectangle, right? So they're saying that the actual area under the curve is going to be the sum of all these rectangles when you let the width tend to 0. How is that equivalent to what I said?
Because you're saying the number of rectangles is infinitely smaller.
Right, and that would mean that the width would have to be infinitely small. Right? So me saying n going to infinity and them saying delta go to 0 is exactly the same thing. Right? So this is the answer to number 1, if you want to write this. As you might guess, I prefer my 4-step process that I wrote last time for the answer. But if you write this, obviously I cannot mark it wrong, right? So, questions about the definition? Last time we spent just too long of a process trying to get 1/3 for the integral from 0 to 1 of x squared. It just took forever. And I hope that it gives you some appreciation. Took forever because we used the definition. We needed to do some research and all of that other stuff, right, in order to figure that out, right? And so, of course, you know, hopefully there's an easy way, right? And we're going to discover that easy way today. Okay, so so this, by definition, difficult. So we would like to do it by theorem. All right, and this is what mathematicians do. Mathematicians want to come up with an easier way to do things. We call those things theorems. Okay. Let's do some very basic properties of the definite integral. Okay, and here's some basic properties before we get to the theorem, the fundamental theorem. The basic properties of the integral. Hopefully they're here, and I can just copy and paste them, right? So, properties of definite integrals. All right. Now, evaluating definite integrals, you have to use the definition at this point, all right? And we did that last time for x squared. All right. So, the first one is that the integral from b to a of f of x is the negative of the integral from a to b of f of x dx. That's the first one. And then the second one is that the integral from a to a of f of x dx is nothing. These are definitions. So if we say the integral, what's the integral from 1 to 0 of x squared? What is it? It's negative 1/3. Okay. He's actually using it. That's good. He was looking at the screen. That's good. It serves a purpose. One person has used it. Right? And then again, these are definitions. Why does it make sense that this is true? The integral from a to a, let's use a concrete example, not that it really matters. But the integral from, and let's use x squared again, from 1 to 1 of x squared dx. What dimension is that in? That's in one dimension. That's a one-dimensional thing. What's the area of a one-dimensional object? 0 for sure, right? The area of a line is nothing. Okay? So we're just trying to find the area under x squared from 1 to 1. Not a lot going on there. Okay? Some other properties. The integral of sum. The integral from, where are they written? Let's just get to it. Here we go. Right, so the integral from a to a of f of x dx is nothing. The integral from b to a of f of x dx is the negative of the integral from a to b of f of x dx. Let's go ahead and say why all of these make sense, okay? 3, the integral from a to b of f of x plus g of x dx is the integral from a to b of f of x plus the integral from a to b of g of x. Let's say that in word. Why is that true? The area under f plus g should be the same as the area under f plus g should be the same as the area under f plus the area under g. Questions about that? So if I want to evaluate the integral of two things, I can just integrate each one separately. This one? Right. If the area under f is 30, then the area under 2 times f is just 2 times what? Right. So if the area under f is 30, what's the area under 2 times f? It should be 2 times 30. Okay. So that if I'm multiplying by a constant on the outside, I can just hold the constant, find the area, and then multiply by the constant afterwards. Okay. I should take that one out. Let's do this again. Say that in words. Okay, so the area under f plus g is the same as the area under f plus the area under g in words. Right? Questions about the first four. What's the fifth one saying? The area under f from A to B should be the same as the area under f from A to C plus the area under f plus C to B, no matter what C is. That makes sense. So that for this one at least, we can draw a picture of something like this. That if we have the integral, we'll draw the picture. So we'll do something like this, right? So is that vertical? Okay, there we go. Right, so you got something like this. Right, so we're going to find the area there. So, well, that's a bad color. So, whew, didn't mean to do that. Oh, well, let's undo that, right? Can we undo that? No. Oh, no, it's not going to do that. How do I get back to one page?
Click one of those, yeah.
One of these?
Yeah.
No. Is it this? Oh, okay, there we go. So, we got this thing, okay? And then, you want to know this area, okay? Well, if you want to, and this is A, and this is B, well, if there's any justice in the world, and particularly if our function is continuous, then no matter what C you pick, you want to find the area from A to B, then you can find the area from A to C, and then the area from C to B. So again, I've been saying, you know, as long as I've been teaching mathematics, that literally it's just another language, right? So that when you look at the symbol, right, your own words, got to make it your own thing. Okay, you're thinking it's the area under the curve, right? That's what this symbol means. It's the net area. Okay. So hopefully, just translating this, and again, this scares people. Number 5, 1 through 5 scares people. The only reason why it scares people is because those people just don't understand the language well enough. Right? Literally, Chinese scares me, right? Because I don't know this shit. I don't know Chinese. Right? That's why it scares me. I don't know the language. Right? So if you know the language, it doesn't scare you. Okay? That's why we're translating. We're trying to translate well. Okay? And then the function, the absolute value of f, if you can calculate the integral under f, then you can calculate the integral of the absolute value of f, right? And so then the absolute value of f makes all that was negative positive, okay? And so the classic example is if we take something like, let's do something like x cubed, okay? And so if we we'll plot x cubed on the interval minus 10 to 10, along with the absolute value of x cubed. So then, I think those are just bars. Let's see how good it is. Will it just take bars? Doesn't know that it's a bar? Let's see. We'll test it. Plot that. All right. So, and let's just do sine. Sine makes it more clear. So sine of x, and then the absolute value of the sine of x. Okay, is my syntax good? Let's put bars around this. All right, so there's a bar there. If I don't put anything for the domain, it goes from minus 10 to 10, okay? Okay. So sine of x is in red and it's doing this, okay? So sine of x is in red. It's doing that, right? The absolute value of the sine of x is going to be the sine of x, but then it's got to be positive. So then absolute value sine of x does this, and then the absolute value is like, no, 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 it can't be negative. Got to make it positive. Absolute value of sine of x. Okay, so it does this. Okay, so it's the green one. Stays positive the whole time, right? So that the integral from a to b, in this case, the integral from minus 10 to 10 of the absolute value of the sine of x is just the sum of all of these areas. Okay. Now, from minus 10 to 10, right, if we get rid of this, if we just look, if we get rid of the absolute value of sine, right, I think that does it. If I just plot that, tell me the area. What's the net area of this one? 0. Do we see that all the positives and negatives cancel each other out? Right? But that's certainly not true of the absolute value of the sine of x, right? If I give you a positive function, right, and maybe I'll get some extra credit. Suppose I gave you a function that was always above the x-axis. Is the integral positive or not? It's positive, right? So if I give you a function that's always positive, the integral is positive. If I give you a function that's always negative, the integral is negative. Okay? Let me go ahead and give some extra credit here. Has to do with what I just said, right? So we know if f of x is positive, this of course implies that if I integrate f, then that has to be positive. If f is always negative, then that implies that the integral is negative. And this is on the whole real line, right? This is on some whole interval. This is on the interval a to b. So if it's positive on a to b, there's no way the integral could be negative. No way. Because all the rectangles you construct are all positive, right? And similarly, if it's always negative, then every rectangle you create from f, the height is always a negative thing, right? And then you add them all up. It's a bunch of negative stuff. Okay. Here's my question to you. Suppose I told you that f of x is continuous and that it was never under the x-axis. It was never under the x-axis. Okay. So it's greater than or equal to 0. Okay. Always. Right? So sometimes it hits 0, right? But it's always either 0 or above the x-axis. Right? And I'm going to add one more thing. And I told you that the integral from a to b of f of x dx is flat out nothing. Okay. What must we conclude about f of x? What must f of x be and why?
So it's always positive, but
It's always 0 or bigger. And I tell you that the integral, the area under the curve, is nothing. Then what must we conclude about f? And say nothing. I want you to think about that. Okay. All right, but it has to do with this. Okay. So let me give you a hint here. Okay. About continuity. Here's a statement about continuity that will help with the y part, okay? Here's a hint. Or actually, this is a remark. I'm technical with my terms, I'm sorry. Here's a remark. If f is continuous, and I told you that f of a was not, suppose I told you that f of a was positive. If I told you that f of a was positive, then there is an entire interval around which f is positive. That makes sense. We'll draw a picture in just a second. I'll have you write down this statement. But if f is positive, and I told you, if f is continuous, and I say f is positive at 4, then I know there's a whole interval around 4 where it's positive. It just can't be positive at 4, and then all of a sudden be completely something else. Right? Why is that? Let's see. Uh-oh, the great skeptics come in here. All right? And so the great skeptic is a person who just doesn't believe anything. You have to prove everything to the great skeptic, okay? And the great skeptic is the most important person in a math class, right? Because again, you're not supposed to trust anything that I say without proof or without a reference to a proof somewhere, okay? Why is this true? So here, let's make A here. I'm going to put A here, and I have a continuous function, f, right? On as a matter of fact, we use A to B so often, so I'm going to use, I should have used C, I'm sorry. I'll use x to y, okay? So from x to y, here's x, here's y. F is defined on x to y, and here's A, which is in between. Okay. Now f is continuous, okay? So I'm going to start here, and I'm going to end it here. Oh, I'm sorry. I'm going to start it here, and I'm going to end it here. I really don't care. So f is continuous. You need to connect this point to this point. And now I'm going to tell you that f of a, I'm going to put it in blue, f of a is positive. Now, all I want you to do is draw a function, right, continuous from here to here, goes to this point, but is only positive at that point. Only positive at that point, so that there's no interval around it, right? So there's no interval around A for which it's positive. It's only positive at that point on this interval. Why can't we do that? Because then it wouldn't be continuous. That's right, right? Because in order to be continuous, what does continuous mean in your words? It means you can draw the function without taking your pen off the board, right? So that's impossible to do in this case, right? So if you draw this, right, I don't know what the hell to do here. I don't know what to do. I need to, all right, so I need to do something like this, right? I've got to do something like that. And that violates the fact that I needed it to be continuous. Okay. So, if it's positive at one number, it's positive on a whole interval around that number. Right. Right. So that helps with why this has to be a certain thing. Anybody knows? Anybody has an idea what this is? You got a function that's always above the x-axis. The area under it is nothing. The function has to be zero the whole time. Okay. So the function has to be 0, and now you just have to explain why it's 0. In order to show that something's 0, we'll prove it by contradiction. Okay. Well, if the great skeptic comes in and the great skeptic says, well, I don't think it's 0. You say, if you don't think it's 0, then you think that there's at least one place, let's call it A. There's one place where it's not 0. Right? And if there's one place where it's not 0, that means there's a whole place where it's not 0. If there's a whole place where it's not 0, then that place certainly has a something. 0, no, not 0 to 10. The obvious answer is 10 there. Even or odd, Wortman. Even or odd. Even. We'll make it worth 6 points. I'm going ballistic on the extra credit already. All right, so that's 14 points. Again, your explanation's got to be flawless. Perfect. Right? So come see me, not one exclamation point, you know, in the wrong place or anything. Okay? All right, so that's 14 points already, right? Okay. Let's do the day of the exam. All right. Oh, let's go ahead and do some of these. Let's knock these out. Properties of the integral. Suppose I told you that the integral from 0 to 7 of f of x is negative 10. What's the integral from 0 to 7 of 2 times f of x? No. Negative 20, right? So a is negative 20. I'm not being an ass by saying no. It's just not right, okay? If the answer is negative 20, you say 20, that's wrong, okay? The integral from 5 to 7, right? It's a little bit more tricky. All right, so let's take this one. Oh, that's no good. Let's try that again. Why did it leave me? No, cancel. I'm sorry. Negative 13. Okay, so the integral of this is negative 20. Just multiply by minus 2. Hold the 2, and then multiply by it afterwards. Okay, so I'll be good. Okay, so this is equal to 2 times the integral from 0 to 7. Just pull the 2 out of f of x dx. That was given to be negative 10. Whew. And that equals negative 12. All right. The integral from 5 to 7. This is a 5 here?
Mm-hmm.
Okay, so that's a 5. No, A. I apologize. The integral from 5 to 7. Well, we know that the integral from 0 to 7 of f of x dx is equal to negative 10, right? That's negative 10. How are these related? Well, the integral from 0 to 7 of f of x is for sure equal to the integral from 0 to 5. Absolutely. Yeah, who said that? Very good. Plus the integral from 5 to 7 of f of x dx. There's only one of these things we don't know, and funny enough, is the thing we're looking for. Okay. So this is given to be negative 10. So classic thing we're doing, using what we know to figure out what we don't know. This was given to be 3, and therefore this is exactly what you said, negative 13 for sure. Right, so then it's negative 13. So we're just using what we know. Say it again, I'm sorry? The next one, right, the integral from 5 to 0 is just the negative of that, so that's negative 3 for sure. Someone wants to just get going, let's do it. The integral from 7 to 0, 6 times f of x. 60. All right, let's not be speed demons. Right. And the integral from 0 to 7 of the absolute value of f of x. Not clear. Can't do that one. Right. Only because the absolute value, right, makes all of these things positive. Let's come up with some good examples here, right? So if I said, let's do a good example. We did the sign, right? So what if I told you that it was 0? Would you think the answer was 0 then? Right? Remember we just did the sign? Let's put it back up, right? If you're going to use the same logic by just taking the absolute value of 10, right? So what people want to do is, if they want to take, I got to go to the right place. If they want to take the integral of the absolute value, people just want to take the absolute value of negative 10 and just make it positive, right? But if you're going to use that logic, then you believe that the integral of the absolute value of sine of x is also 0, but that can't be true because the absolute value of sine of x makes all of this positive. This is a bunch of positive stuff. Okay, so you just can't take the absolute value of the answer. Okay, what some people are doing is that they're just taking the absolute value of this number, but that would be this, right? It's not the absolute value of the integral from 0 to 7 of f of x dx. Right? That for sure is 10. Right? But the integral of the absolute value is something, it could be anything. It could be anything.
So the only reason it's unknown is because we don't actually know what the function is.
That's right.
If we had the function,
If we had the function, we could
then
figure it out. Yeah, that's right. All right, questions about these properties? Questions about these properties? Okay. Let us go ahead and move on to the fundamental theorem of calculus. I don't know why it's not happy with me here. Oh, because that's there. Okay. Fundamental theorem of arithmetic. What is it? What's the fundamental theorem of arithmetic? The fundamental theorem is in every single important area of mathematics. Okay. The fundamental theorem of arithmetic says that I could do something with 36. Right. The number 36 I can break down as the product of what? Anyone know fundamental theorem of arithmetic? I use 10. 10 is equal to what? If I factor it. 2 times 5, right? 8 is equal to what? 2 times 2 times 2, right? Right. What about 22? 11 times 2. What's true about 2, 5, and 11? They're all prime numbers, right? The fundamental theorem of arithmetic says that every single positive integer can be broken down into the product of prime numbers. Okay, that's the fundamental theorem of arithmetic. And it's actually used that to prove that there are infinitely many prime numbers, which is extremely important for us. If we didn't know that, then we wouldn't be able to buy anything on Amazon.com. Okay. It's true. We use prime numbers in order to code credit card numbers. Okay. The fundamental theorem of algebra says that if you have a polynomial of degree 3 and you set it equal to 0 and solve, including repeats and including complex numbers, how many solutions are there? 3. A polynomial of degree 3, if you set it equal to 0 and solve, then you got to get 3 answers. If you have a polynomial of degree 35, set it equal to 0 and solve, you have 35 answers. Okay, that's the fundamental theorem of algebra. Right? As a matter of fact, you use the intermediate value theorem to prove that. Okay. The fundamental theorem of calculus unites the integral and the derivative. Okay, and so it is question number 3 on the exam. State the fundamental theorem of calculus. All right, and I think it's going to be question number 1 the rest of the way. Right. State the fundamental theorem of calculus. Now, our goal for Chapter 5 is to just calculate area after area after area. This is what we would like to do. Now, at the end of Calc 1, you were supposed to have done this over and over and over again. I'm giving you a crash course for the end of Calc 1. Right? So what we were supposed to do, I was supposed to haze you, okay? I was supposed to make you calculate area after area after area until you literally started begging me and say, please, Dr. Winger, there's got to be a shortcut. Right? That's what I was supposed to do. Okay? And hopefully that's what happened to you at the end of Calc 1. Okay? So that now we're going to get to the shortcut pretty quickly now. Okay? Because it gives you appreciation for being a part of the group that can use the shortcut. Right? That's what I mean by hazing. Right? So, okay, so let's look at sine here, right? We know that the integral from minus 10 to 10 of sine is 0. Let's start at 0. So the absolute value, I'm going to leave the absolute value off, but let's go, I'm going to start at 0. 0 to 1, okay, so I don't need that extra one, right? And I need to put x, right? This is a statement about x. Okay? I'm going to use cosine because cosine is easier for this example. There's the cosine of x. Okay. I want to know that integral. Right? The integral from 0 to 1 of cosine x. Now, we can get our rectangles together and do all of that stuff, right? But it's not trivial to see what the answer is going to be. And remember when we did x squared and we went through and calculated all the rectangles, there was a point in which we needed to do some research about formulas, right? To see what that limit was going to be. And there is no formula here for cosine when you get to that same point. So this is really a hard problem when you want to know the exact answer, right? We can only approximate this if we don't have any other method. Just by using rectangles, we can only get an approximation. All right. But I want to be good. I want to know the integral from 0 to 5. So the great student has walked in, right? And the great student comes in, and the great student just keeps asking question after question. Remember I said good students ask questions? This person just won't stop, right? So they'll ask me, what's the integral from 0 to 1 of the cosine of x? And, you know, I get my rectangles out and give them a 10 decimal approximation. And they say, what's the integral from 0 to 4? And I get more rectangles out. And I calculate that, right? And then they want to know what's the integral from 0 to 10, right? And I say, wait 1 second, right? I need to figure some things out. Okay. I can't just keep doing this hand by hand, right? So literally, we want to know what's the integral from 0 to t. I just want to end his questions. I just want to end it, right? I'm going to switch the letters up on you, okay? I want this to be t, and I'm going to call the other one x. Okay, so t goes from 0 to x. Right. So we're going to call this an area function. And all it does is measure the area. And all it is if you have a function f, and so here's, so given a function f of t on the interval a to b, then a of x is simply measuring the area up until x. That's all it does. Questions about that? And so for the easy ones that we had before, right? So here, let's do a of 1 I have a space there for some reason. A of 1 is that number, whatever it is. I have no idea what it is. Okay. A of pi is that number. What do you think it is? What is A of pi for this? 0. A of pi is 0. What is A of 2 pi? You have an idea? A of 2 pi? 0. This area and this area cancel. Okay. So whatever this relation is, it seems like it's 0 at pi, 2 pi, 3 pi, 4 pi. Right? It seems like it's 0 there. Right? What is it at pi over 2, I wonder? Right, so then I need to divide this by 4. Right? It's that. What do you think that is? It's not 0. What is it?
1.
It is 1. It is 1. I get all my rectangles together, add them up, I'll get something closer and closer to 1. Right? See, he was able to do that so quickly, right? All right. So for this function, let's use this one in particular. Okay. So for example, right, so for f of x equal to the cosine of, well, let's use t. For f of t, equal to the cosine of t. I'm going to construct the area function for that one, and all it is the area under cosine. I'm going to be on the interval from 0 to whatever. Right? So from 0 to x of the cosine of t dt. We know that a of pi, at least from looking at it, a of pi, nothing. A of 2 pi also looks like nothing. The claim is that a of pi over 2 is 1. We know a function that does that already. Interesting. We know a function that's 0 at pi and 2 pi, and it's 1 at pi over 2. That is sine. Right, it looks like a, at least at, there are infinitely many numbers on the real line. We've taken 3, and this one has 3 points in common with sine. Okay, so that's not enough evidence to suggest that capital A is sine. Okay, well, we'll plot them together. Okay, but any question about what this is? All it is measuring the area under the cosine. So let's just take this a little bit farther. Okay, so suppose I went from 0 to 10, and then I want to look at the area. All right, so from 0 to 10. Okay. And so there's the cosine, and now before that, I think I want to insert. Will it insert before? No, it's only going to insert afterwards. So, but I want to do this. I want to calculate the area. So I want A to go from x to, and Maple's nice. It has the integral. I want it to be the integral of the cosine of t, and then I want t to go from 0 to x. Maple is just ridiculous like that, okay? So there's the area function. I've called the capital A. Okay, now, as you know, I want to plot that along with the cosine. All right, so now I'm going to plot capital A of x along with the cosine of x. All right, so I need to put that in brackets because I'm plotting them together. Okay, so I'm measuring the area. We got to make sense of this. And then x equals 0 to 10. Okay? Let's plot them together. Okay? Which is which here? The green one is, the green graph is cosine. At 0 it's 1. At 0 it's 1. There's no way the red graph could be cosine. No way. Because cosine is 1 at 0. It's 1 at 0. Okay? Now, the red graph is the area under the green graph. Right? So it's not so surprising that on the green graph, as we move to this point, the green graph, you're getting more and more area under the green graph. Is that okay? And therefore, the area under it is increasing because I'm adding more and more positive stuff. At this point, it looks like, well, now I'm going to start adding negative stuff to this area under the green graph. And that means that the area has to start decreasing for sure. We already said that at least under the green graph, it's all positive here, and then all this negative stuff. What happens at this point in terms of the area? It cancels. All this positive area under the green graph with this negative area under the green graph, right? They cancel, and therefore the area under the green graph from this point to this point should be 0, and A is 0 here. At this point, we're still negative, and therefore the area is still going to be negative, right? Very negative. And then finally, after this point, we start adding some more positive stuff, and then it becomes less negative, 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 and again, we're 0 at this point. Okay, so capital A is just measuring the area under the green graph. We should also recognize that capital A is the sine curve. Okay. Capital A is the sine curve, and that is the fundamental theorem of calculus. Okay. Now, in order to demonstrate that, I like using the pigeonhole principle. The pigeonhole principle says that if you have, for example, you'll learn this in discrete. It's one of the most important theorems in discrete. It says that if you have 2 boxes and 3 items, and you need to place all 3 items in the boxes, then at least one box will have 2 items. That's the pigeonhole principle. That sounds so trivial, right? Isn't that so trivial? But it is the most important theorem in discrete mathematics. Okay. So now I'm going to put up 3 graphs. There's A, there's cosine, and there's sine. 3 graphs. I'm going to plot them. Only see 2. Only see 2 graphs. 2 of them must be the same. And we know cosine is unique. Cosine is the only one that starts off at 1. And therefore, sine and capital A are identical. Okay. Questions about that? About the Pigeonhole principle? What relationship does sine have to cosine? The derivative of sine is cosine, right? So the remark here is that capital A of x is the sine of x. Okay. The fundamental theorem of calculus in words says that the area function is an antiderivative. The area function is an antiderivative. If you take the derivative of the area function of some other function f, then you get that function. Right? That's the remarkable thing about the fundamental theorem of calculus.
Is that what we have to write for the exam?
I'm going to say state the fundamental theorem of calculus and write in words what it means. Write in words what it means. And in words, it means that the area function is an antiderivative of a function in question. Right? Here's the fundamental theorem of calculus. And the book has 2 parts. Let f of t be continuous on the interval a to b. And let capital A of x measure the area under f from a to x. Now, I've been biased already, or I've tried to hand wave this enough already. Now, I haven't even said anything about capital A yet. Is capital A a function? Is capital A a function? If I'm measuring the area under f, right? Got so many windows open. If I measure the area under f, if I change the place, will I get a different area? If I change x, will I get a different area? Yes, right? So if I have a different area, will I have a different x? Yes, maybe, right? I can get 0 multiple times, right? But the point is that for each x, there's only one area. For each x, there's only one area. Is that a function? Yes. Right? So capital A is a function, right? So if you want to be anal about it, that was the first thing you should have asked me, right? Because I said capital A is this function, and you say, wait, why is it a function? That's the first thing you should have said. Okay. So capital A is a function, but even more important than that, it's smooth, and you can take a derivative, right? Then the fundamental theorem of calculus says that the derivative of capital A is what? F of x for sure. Derivative of A is f of x. That's the fundamental theorem of calculus. Now the book has a part 2, but part 2 follows directly from that. So this is all that I need. Right? I'm about to talk about part 2 in just a second, but this is the fundamental theorem of calculus. Questions about that? Here's the major consequence. So the major consequence is this. Now that when we want to find, remember, this is what we want to solve. We want this. How in the world can we figure this out? I want to know that. Okay. So here's what I'm going to do. I'm going to let capital A of x again be equal to the integral from a to x of f of t dt. Okay. So how do I figure this out? What do I know about this? Then, by the fundamental theorem of calculus, capital A is an antiderivative Is that okay? I want to just remark that about A of B. What is A of B? Wherever there's an x, I put a b. So what is it? It's the integral from a to b of f of t dt. Right? Tell me what a of a is. Very good. It's the integral from a to a of f of t dt. And we've already said by definition that that's nothing. Right? So automatically, capital A and the question we need to answer are related. Right? Because if you put in B, you get the thing that we need. Okay? There's a remark from Calc 1 that we'll need. I'm sorry, I went too far. Go back. I want to extend the page. Here's the remark from Calc 1. I guess I should say that remarks are important. If I ever say, here's a remark, it'll be something that you need. Okay. If two functions have the same derivative, right, then what do we know about them? Two items are moving at the same rate. What do we know about those two things? So I'm running 2 miles an hour, you're running 2 miles an hour. What do we know about the difference between us? It's not the same. No, well, the difference between us is constant. I like it. That's right. The difference between us is constant. Right? So that means that if I told you if f prime of x is equal to x, let's do 2x. 2x, and g prime of x is 2x, then what we're saying is that f of x minus g of x has to be a constant. Two functions have the same derivative, then the difference has to be a constant. What does that mean? That means that if I and Gabe are running, right? He's running 3 miles an hour, I'm running 3 miles an hour. We may not have started at the same place. If we started at the same place, we would be at the same place the whole time, right? But if we're both running 3 miles an hour, then for sure, he's not running away from me, and I'm certainly not gaining on him. The difference between us is constant. We just stay right with each other. The difference between us is constant. Right? That's all we're saying here. Two functions have the same derivative. The difference is constant. That's a constant. This has some implications. Particularly, it says something about x squared, that every single antiderivative of 2x must be x squared plus some constant. Right? That if any function has a derivative that is 2x, then the function has to come from x squared plus something else. Okay. That's the remark. Okay. Well, what does that have to do with this? Okay. So again, if I want to know how to figure this out, then I know that this is an antiderivative, but I know if I take any other antiderivative, right? So now, going back to red, taking any antiderivative capital F of little f from the remark, we know that capital A of x minus f of x has to be constant, and therefore capital A of x is equal to f of x plus a constant, where f is an antiderivative. Okay. And so finally, we have that the integral from a to b of f of t dt is equal to, okay, here's the magic. This is equal to, we already said it, this is capital A of b. Right? But that's also capital A of b minus capital A of a, because capital A of a was 0. Okay? But that's equal to, well, what's A of b? A of b is just whatever you would get if you put a b here. So that's capital F of b plus a constant minus capital F of a plus a constant. And what happens to the constant? They cancel. And this is F of b minus F of a. So if you want to know the integral from a to b of little f, all you need to do is find any antiderivative, evaluate them at the endpoints, and subtract. That's how you calculate the area under any curve. If you can find an antiderivative, plug the endpoints in the antiderivative, subtract, and that's the area you need. Okay? So, I'm going to take any questions on that. I need to keep this up.
So find the endpoints, plug them in, and subtract.
Into the antiderivative. You want to know you want to find any integral. If you can find the antiderivative, then the integral question is over. Right? And so again, that long struggle that we had, here's the extra credit that I gave to you. The integral from 0 to 1 of x to the third dx. I claimed I wanted you to show to me by definition that that is 1/4. We'll do it in an instant now. I need a function whose derivative is x to the third. Give me one. 1/4 x to the fourth is an antiderivative of x to the third. So for, in this case, f of x is x to the third, and capital F of x, which is the antiderivative, is 1/4 x to the fourth. Now, I could put plus a constant. Why don't I need to do that in this case? Because what happened in the proof? What happened to the constants? They cancel. So I don't have to put the constant. So there's the antiderivative, and so the answer is 1/4 times 1 to the fourth minus 1/4 times 0 to the fourth, and that is 1/4, and that is the end of the game. One line. Okay. No rectangles, nothing to do like that. Okay. Questions about that? So, questions about integrals are really questions about antiderivatives. An integral is presented to you and say, okay, I want to find this area. First thing we say now is, oh, Can I find an antiderivative of this? If I can, no problem. If I cannot find an antiderivative, then what do we have to do? What do you have to do if you cannot find an antiderivative? Begins with an R. Right. You have to do the Riemann sums. You have to do rectangles. I was actually looking for rectangles, but right. So you have to do a bunch of rectangles. Okay. All right. So chapter 5, and particularly chapter 7, all antiderivatives. The whole chapter is about finding antiderivatives. And if you can remember, chapter 4 in Calc 1, if you've had it here, all about derivatives. I'm sorry, chapter 3, all about derivatives. Okay. Chapter 7 in this course, we spend the whole time just trying to figure out how we can find antiderivatives. And the reason is because if we can find antiderivatives, then we can find integrals. Chapter 6 is about applications of the integral. Okay, but chapter 7, just about antiderivatives. And you can see why we need them. Okay. It makes it much easier. 5.5 talks about the substitution method, which is the most common way of finding antiderivatives. Okay. So, notation. I keep saying antiderivatives over and over again. Right? For a function f, f of x, we denote the antiderivative by this. This is the notation for the antiderivative. So notice that there's no a or b or anything like that, okay? So we call that an indefinite integral. An indefinite integral. So we already have some examples. So the antiderivative of x to the third we just did. Now if it's indefinite, I would need the constant. It's 1/4 x to the third plus a constant. Notice the difference between the two problems I did. I wanted to know the integral from 0 to 1 of x to the third dx. I'm literally asking for what is the net area under the graph of x to the third from 0 to 1. That is a stone cold number. That's a number. But then when I write this notation, I say, well, what is the antiderivative? When I write this, I'm literally saying, what is the antiderivative? I'm asking, give me every single function. This is a 4, right? Give me every single function whose derivative is x to the third, and this is every single one. Yes, this is how we write it. Because we would have to write 1/4 x to the fourth plus 2, 1/4 x to the fourth minus 18, 1/4 x to the fourth plus 999,472. Right? I have to write them all. And so the way to write them all is to just add an arbitrary constant and say that constant can be anything. Okay? Okay, so notice the difference between these two things. This is a number. This is infinitely many functions. Okay. By the way, this remark is a result of the mean value theorem. This is because of the mean value theorem. Okay. All right, so the antiderivative of x squared dx. Right, this is what we did in class. We did the integral from 0 to 1 of x squared dx, right? And so now that is 1/3 x to the third plus a constant. And you know what I'm about to do, right? We've already done 2 of these. We need to do them all. Right. That's how mathematicians work. In general, the antiderivative of x to the n is what? 1 over n plus 1 x to the n plus 1 plus a constant. Okay. This is true as long as n is not what? negative 1. We don't want to be divided by negative 1. The great skeptic, of course, says, well, you know, what happens at negative 1, right? But now we know that the function 1 over x, when n is equal to negative 1, right, then you get x to the negative 1, and that's 1 over x. And we know for lots of reasons why that 1 over x is pretty important to us, okay, because it's usually the way that we talk about the demand function in economics. X equals 1 to 10, right? I need a comma. Why is it not happy with that? Plot 1 over x. Now that's good. Do I need a space? Huh. I'll try it again. Plot 1 over x. X equals 1 to 10. Okay. So the demand function. Okay. As price increases, demand for it decreases. I want to know total demand. I want to know total demand. I want to know the integral from 1 to 10 of 1 over x. Right? So we just can't say that when n is negative 1, we can't answer the question, right? We do want to know what that value is, right? What is the integral from 1 to 10 of 1 over x dx? Oh, we need a function whose derivative is 1 over x. That's the natural log of x. That's right. That's the natural log of x. And here's notation. We're going to put in 110 and subtract. That's my notation for it. It's the natural log of 10 minus the natural log of 1. And of course, we know in our sleep that the natural log of 1 is 0. So it's the natural log of 10. The total demand is the natural log of 10. Okay. Questions about that? So when n is equal to negative 1, we already have an answer there, okay? All right, so that's a couple of antiderivatives, but now on the first day we did all of our derivative rules, and now there are a bunch of antiderivative rules, okay? So we'll go ahead and roll through them, right? Beat me to the answer. We need to reverse all of these. The antiderivative of x to the n, we've written that one, is equal to 1 over n plus 1, x to the n plus 1, as long as n is not plus a constant. As long as n is not negative 1. The antiderivative of 1 over x dx is the natural log of x plus a constant. And I got to be technical here. It's the natural log of the absolute value of x. Okay. Let's go ahead. For some reason, this here implies some other things that people don't see pretty quickly. Let's go ahead and put it. The antiderivative of 1, the function whose derivative is 1, is what? X for sure. X plus a constant. The antiderivative of 0 is just a constant. The antiderivative of e to the x is e to the x for sure. So now all I want you to do now is go through and finish all of these, right? And so then the antiderivative of secant squared x dx is tangent. The first question I asked in this class was, what's the derivative of tangent? And then half a person said secant squared. Right. I had also said that why, for a class that I had already said was about the integral, why was I asking you about derivatives? And this is the reason. Right. Why was I asking so much about derivatives in a class in which I said it had everything to do with the integral? And it's because we need to know antiderivatives in order to do integrals. And that requires that you know derivatives. Okay.
Can you scroll up for 1 second?
Thank you. Now we can go ahead and do it. We can, question number, what is it, 5? Are we already on 5 or is it 4 on the exam? 4. Question number 4 in the exam. We can just do these basic antiderivatives, okay? I'll just put a bunch of them up there. So let's make that question number... Have I labeled the other question? Yeah, I did, right? The fundamental theorem of calculus. I said that was a test question, didn't I? Didn't I write that down? I don't think I wrote it. Let's write it. And that's question 3, right? I said last time again, you have to wonder how everyone just doesn't get an A in this class. And it's just because of effort. It's just effort. Okay. The B's and C's of the people somehow with other things going on. And I can understand that. Because, you know, calculus can't be the center of your world. Question 4 on the exam. Let me go ahead and tell you to finish these. Okay, so finish. Fill in the rest. So I'm just testing the basic ones here. So the antiderivative of 1 over the square root of 1 minus x squared. What's the antiderivative of minus cosecant x cotangent x? What's the antiderivative of sine x? Trust me, we'll get to the harder ones soon enough. The antiderivative of 1 over 1 plus x squared. That's what the question's going to look like. There might be a ton of these. Usually my questions only have 3 or 4 parts, but this might have 7 or 8 parts. Only because this is just read off. Like, if you know derivatives, then I'm just giving these away. Please. Absolutely, thank you. So as we've already said, this is really a question about, do you know the derivative functions well? All right. Write the answers, please, and then we'll get through this. Here we go. That's what you got to turn back. See, that's fine. We're still in turn back time right now. Just don't be in turn back time the day before the test.
What's the last one?
Thank you. Always. That's an inverse sine of x. Please. Right. I'm sorry? Cosecant. Cosecant. Okay, it's all good. Negative cosine. And tan inverse is right. Who said that? You said that, right? What is your major again? No. A man after my own heart. I absolutely love it. We'll talk about advisors after the course, after class. I have a recommendation. So, questions about this and questions about what I'm asking for a question for. All right. Let's do the substitution rule. Let me say that roughly I've gone pretty fast. Now, if you feel like I've gone fast through the covering of the integral, there are a couple of reasons for that. The major reason is that, again, it's supposed to be talked about at the end of Calc 1. Really, in the syllabus, in the school syllabus, right, for this course, they list Chapter 5. You can look in the syllabus. I couldn't, because there are like so many sections of lots of different courses, we don't get a chance to write our own syllabus, right? But if you look in the syllabus for chapter 5, it says this stuff is to be covered, but in parentheses it says review, right? So this is supposed to be review. Now, before I talked about it, had anyone never seen the integral before? Okay, good. That makes me feel better about who's never seen the substitution rule. All right, wow. All right, here's some pressure. Say it again.
So we're just that great of a class.
I hope so. I hope so. Let me know otherwise, right? But over under first test, over under average, I need like an 88, something like this. Right? If this is all review, who's getting an 88 at least? First test, 1, 2. Whew. This is good. This is good. Miss? What are you thinking? Yes, I'm talking to you. That's right. That's right. Don't bring it down to 87. Don't bring the average down. All right, good. You know, the only problem is going to be on this test. Everyone's going to do these well, but I got a question at the end about concepts. It's just true, false. Do you understand the concepts I've talked about? True or false, the area function of another function is an antiderivative. True or false? That's true. All right, so, you know, some people think I'm trying to trick you. You just need to make sure you understand the concepts. And that separates people from, that separates the A's from the B's. So make sure you understand the concepts. Okay. All right, great. Then we know the substitution rule, right? Every antiderivative rule is matched up with a derivative rule, okay? And so the substitution rule as an antiderivative rule is matched up with what derivative rule? The chain rule, right? And so the chain rule says, for instance, that the derivative of the sine of x squared is what? We did this on the first day too. It's cosine of x squared times 2x. Is that okay? Who remembers that? Fantastic. The antiderivative. I'm about to get on a fast train in a second. This is good. The antiderivative of 2x cosine of x squared dx. Trivial then, right? That's the sine of x squared plus a constant. So that this antiderivative rule goes with this derivative rule. And what we're going to have to do is we're going to have to reverse the chain rule. The substitution rule requires us to reverse the chain rule. One of the things to note is that whatever the antiderivative process does, this 2x vanishes. Right? The 2x vanishes here. The x squared stays. Okay. So what it's going to require us to do is we're going to look at a problem like this. And this is what we do with antiderivatives. The first thing we do is we say, can we use the substitution rule? Is this a substitution rule problem? Okay. And so if it is a substitution rule problem, because the substitution rule is matched with the chain rule, then we have to ask ourselves, is the derivative of something, of some other function in this problem? Right? The reason why we knew this was a substitution problem is because 2x is the derivative of x squared. Okay. Given that, in a very similar way, we should have no problem with the antiderivative of 3x squared times secant squared of x cubed. Again, the chain rule fleshes out the derivative. The substitution rule, going backwards, says I need to get rid of that derivative to go back. Okay. What function as a derivative is this? Tangent of x to the third plus a constant. Tangent of x to the third plus a constant. Of course, you can check that. The derivative of the tangent of x to the third is secant squared of x to the third times the derivative of x to the third, which is 3x squared. All right, so let's go through this in a systematic way. Here's what we would do. All right. So let's go forwards. Well, It all depends on how you count it. We'll go forwards with the derivative and then backwards with the antiderivative. All right, so if I have the tangent of x cubed, we'll put this in a different color. If I have the tangent of x cubed, and I'm taking the derivative of that, then literally we would move to the side and say, oh, I know that the derivative of the tangent of any function, we said this on the first day, is secant squared of that function times the derivative of that function. We know that. Right? So we're going forwards with the derivative. And so what we would do is we would say, okay, it looks like the inner function is x cubed. The derivative is 3x squared. And then we would use that formula. That's what we did in Calc 1. And then we would just say, oh, it looks like it's secant squared of u times the derivative of u. No problem. Okay? That's what we did in Calc 1. Now, we're in Calc 2. Right? I'm now presenting you with the antiderivative of secant squared x cubed times 3x squared dx. Okay. Now, on the side, I know for sure that the antiderivative of secant squared u du is the tangent of u plus a constant. Right, so notice the analog, the analogy I'm trying to create here. Right? I know that the antiderivative of secant squared is tangent. And all I mean by that is this statement. That's all. This just means the same thing as this. That the antiderivative of secant squared du is tangent. Right? So these two statements are equivalent. So now I'm going to do exactly the same thing. Okay, so I'm going to let u equal x cubed. Right? So I'm going to let it be the inside function. I'm going to let u be x cubed, and then I remark, I don't call it u prime, I call it du. Right? So this is Leibniz notation. Leibniz is one of the inventors of calculus. He and Newton got into a massive war about who discovered the fundamental theorem of calculus first. And actually, Leibniz discovered it first. Newton published it first. Right? So there's that whole battle there. But we credit both of those people to being the inventors / discoverers of calculus. Okay, so the derivative of x cubed is 3x squared dx. Now we're calling this the substitution rule for a reason, right? So the whole point is to substitute this, all of this, into this to make it look like this so that we can write the answer, right? Once we substitute, okay, I cannot extend this page anymore. That's my last extension, okay? So now, if we substitute, then this integral becomes the antiderivative of secant squared, well, x cubed was u, and then 3x squared dx is du. But this we know in our sleep. Questions about the substitution? One of the things to recognize is it doesn't matter where the 3x squared was. I put it here. If it was in front, the same substitution would work, okay? So the antiderivative of secant squared is tangent plus a constant. And then you'll just be committed to writing this as a function of x. I gave it to you in terms of x. You have to give it back to me in terms of x. There's no reason to stop at writing this u here. U is x cubed. This is tangent of x cubed plus a constant. Questions about this? All right, so I'm going to give a bunch of homework just doing the substitution rule. Okay. I haven't put any tricks in here yet. Okay. No more sending. No. Otherwise, you'll never. Yeah, when you get that as a PDF, you won't get everything on the page if I keep extending it. Okay. All right. I mean, as you might imagine, that's question number 5. Just chain rule. Okay. I'm sorry. Substitution rule. Okay. So we're talking about a antiderivative of 2x times x squared plus 15 to the 90th. We're talking about, this one was on the final in Calc 1 last year, something like, I think it was x squared sine of x to the 3rd dx. It may have been cosine. Sir. Oh, I'm sorry. He's in another conversation. See, the antiderivative of, let's be bad. Cosine of the natural log of x over x. The antiderivative of, let's do something like, let's do something wicked, like, this is about as bad as it gets, okay? So, about as bad as it gets is, let's say, 3 over 1 plus 9x squared. Do it. You all have seen this before. Do it. I was taking questions as you're going through it. So we'll do these today. Next time we will do a ton more chain rule problems. We'll probably go into My Math Lab and do the sick ones they have there. My Math Lab is usually way more difficult than I'm going to be, but that makes it fantastic practice, right? Because if you do it, you'll be set, okay? And then, we'll practice a lot as well on Wednesday, and then we'll go into chapter 6. So when you're doing the substitution rule, you're picking a value for u, picking a function that's going to be u. And again, if we're doing the anti-chain rule, then we need the derivative of that function to be there. If we're thinking that this function comes from taking the chain rule of some other function, then the chain rule involves multiplying by a derivative, and therefore the derivative has to be there. And it is, right? It's 2x is the derivative of x squared plus 15. Reversing the substitution rule, that means this is u, and that's u prime. This is u, and that's du. Okay. So let u be x squared plus 15. Let u equal x squared plus 15. du is 2x. This is u to the 90th. 1 over 91 times x squared plus 15 to the 91st plus a constant. Was it 15? 15. Let u equal x squared plus 15 from 2x dx. This antiderivative becomes, substituting, it becomes u to the 90th du. And then we already wrote how to do this problem. This is 1 over, add 1 to the power, divide by it, 1 over 91 u to the 91st plus a constant. This is equal to 1 over 91 times x squared plus 15 to the 91st plus a constant. I'll take questions. Antiderivatives. X squared sine x cubed. I'm giving this one just to make the point that you don't need 3x squared here in order for this to work, right? We can be bullies about this and put the 3 there and work this problem out. So u in this case is still x cubed. Du is 3x squared, right? But there's not a 3 here, and we'll just rectify that. Antiderivative of x squared is the sine of x cubed dx, right? U is equal to x cubed. Du is equal to 3x squared dx, right? And we'll be committed. We're committed to removing all the x's and putting u's there, okay? If that's true, then we're going to need to get rid of this, and this, okay? But x cubed is u, so that's already gone. X squared dx, I need to write that in terms of u only. We'll just remark that x squared dx will bring the 3 over here. If the 3 is not here, we'll just move it over here. It's equal to du over 3, 1/3 du. And now we can substitute. Just dividing the 3 over. I know it's been a while. How's this looking? Amanda? Yeah. Okay. So this is equal to sine of x cubed, sine of u, and then x squared dx, again, is 1/3 du. But again, we know what to do with this 1/3. We'll just put it on the outside. Now this just becomes the antiderivative of the sine of ud. So we just pull the 1/3 out. That was one of the first rules that we had from the antiderivatives. In our sleep now, this is 1/3, and then the antiderivative of sine is, what is it? Negative cosine, right? Negative cosine u plus a constant. I can put the constant inside or outside, okay? Being committed to writing everything in terms of x, this is equal to minus 1/3 the cosine of, what was u again? I never remember. X to the 3rd, thank you, plus a constant. So that is the answer. Take any questions about this? 0 to 10 is a difficulty level meter. 0 is, oh my God, I can't believe you asked me this. This is so trivial, easy. 10 being, oh my God, I can't believe you asked me this. This is so difficult. What is this? What is it? A 3, 2, 4, 4. Okay. Let me know otherwise. I'll be asking that for a lot of problems. All right? Cosine of the natural log of x over x. Trying to be tricky, but I can't trick you. I just can't. Cosine of the natural log of x over x The question, of course, is the derivative of the natural log of x somewhere in this problem? And of course it is, right? So we'll just remark that this is equal to this. Multiplying by a number, or dividing by a number is the same as multiplying by its reciprocal. And divided by x, that's the same thing as multiplying by 1 over x. And now it's obvious how to do this problem. Right? You let u equal the natural log of x, and then du is just screaming. It's just screaming at you. Right? It's 1 over x dx. Right? It wasn't so obvious to see in the previous problem, in the previous formation of the problem, but now that you see it like this, it's just play is knocked down the house. The sine of the natural log of x was a constant. The sine of the natural log of x was a constant. U is the natural log of x. Du, 1 over x, dx. This is our last one for today. This becomes the antiderivative of the cosine of u du, the antiderivative of the cosine sine of u plus a constant. And then u again was the natural log, the sine of the natural log of x. Okay. We're going to start off with some of these. We'll do a ton of them. Go into my math lab, and then we'll move on to chapter 6. I'll post this tonight. I'll upload this to the server, and then I'll post it tomorrow.